Dear students, in this video on physical word and measurements, we will study length, mass and time measurements with examples. So let us begin with measurement of length, and here let us first see some of the units used to measure very small lengths. So starting with Fermi, represented by Fm, and it is equal to femtometer, 10 raised to the power minus 15 meter, and it is approximate size of a nuclear size. And if we say Fermi, then we are talking about length only. Like if I write femtosecond, Fs, then it will be 10 to the power minus 15 second. But it will not be called Fermi second. Fermi means length only, that is femtometer. And next one is angstrom, 10 raised to the power minus 10 meter, represented by capital A with a small degree sign over its head, and it is approximate size of an atom. And some example, like wavelength range of visible light is from 4000 angstrom to 7000 angstrom. And next one is micron. Micron is micrometer, mu m, that is equal to minus 10 raised to the power minus 6 meter. And for example, the thickness of human hair is about 50 micron to 100 micron, and size of bacteria is about 2 micron to 3 micron, right? So see, these units are exclusively for length. They are not used for any other physical quantity. And now let's have a look at some of the larger units to measure length, like light year, astronomical unit, and parallactic second called parsec. And let us look at their definitions first. Light year. Now light year is the distance travelled by light in vacuum in 1 year, right? So light year is unit of distance, and it is the distance travelled by light in 1 year. So you know that distance is equal to speed into time. So speed of light is known to us, and time is 1 year. So convert it to second. So now speed 1 light year is equal to 3 into 10 to the power 8 meter per second into. Now 1 year is 365.25 days. 1 day is equal to 24 hour. 1 hour is equal to 60 minute, and 1 minute is equal to 60 second. So multiplying all this, the year is converted into second. And now this speed into time gives you the distance equal to 1 light year, and it is 9.467 into 10 raised to the power 15 meter, which is approximately 9.5 into 10 to the power 15 meter. So light year is a very large unit. And now astronomical unit. Okay. Now astronomical unit, represented by AU, is the average distance between the sun and the earth. So its value is, one astronomical unit is about 1.496 into 10 raised to the power 11 meter, and nearly equal to 1.5 into 10 raised to the power 11 meter. This is smaller than light year. So you can see here the sun and the earth is in its orbit around the sun, and the average distance between the earth and the sun is 1 astronomical unit, 1 AU. Okay, and now parallactic second, or also called parsec. Parallactic second is the distance at which an arc length of 1 astronomical unit subtends an angle of 1 second. So let's try to understand it. Here we have an arc of length 1 astronomical unit, and see, yeah, we have this arc of length 1 astronomical unit, and it is subtending this angle 1 second at this distance called 1 parsec. So if you can have a look at this now, see, 1 astronomical unit is the arc and the angle is 1 second, and this distance is parsec, right? And let us find out its value. Then let's go back to the previous slide. Yeah, here. Now you know that angle is equal to arc upon radius, and the angle here is 1 second, so it has to be converted to radian, and you know that this 1 second will be equal to pi upon 180 into 60 radian, and this arc is 1 astronomical unit, which is 1.496 into 10 to the power 11 meter. So put the value of angle here and arc here. You can calculate this radius, and this radius is equal to parsec. So calculating all this, 1 parsec comes out to be 3.08 into 10 raised to the power 16 meter. So this is larger than light year and larger than astronomical unit. You can see, yeah, 3.08 into 10 to the power 16 meter. And now relation between parsec and light year, you can see 1 parsec is equal to 3.26 light year. So these are some of the larger units used in astronomical studies. And now measurement of large lengths. So if you want to measure very large distances, we use a method called parallax method. So let us try to understand it. The position of an object appears to change when the position of observation changes. Now this effect is called parallax, and the distance between points of observation are called bases. It is like you want to observe this point P, and this point this point P is observed from two different points. When it is observed from this point, it appears along this direction, and when it is observed from this point, its position changes. Point P is observed from this point L, and its direction is along this, and the same point is observed from this point and the direction changes, and this angle is called parallactic angle, and the distance between these points of observations is called basis, and the angle you can see this angle can be measured, the distance of observation can be measured, and if you know these two things, we can measure the distance of this distant object. So let's see what we do here. If the object P is observed from points L and R, then parallactic angle theta is equal to this arc upon the radius. Now this is equal to LR upon PL, and that is equal to B, the size of basis upon distance D. And using this relation, we can find out this distance very easily. So this method is called parallax method, and we can use this method to find distance of distant planets and stars and moon, etc. So let us see how we do it. So finding distance of a distant planet or moon using this parallax method. So here moon is placed at this point, and if you are on Earth and see you observe this moon from point L, and then you observe moon from point R on Earth, and you can measure this distance between them, the basis B, and then this basis B can be measured, you are on Earth only, and this angle theta can be measured, and using the relation the distance of moon can be found out. So here the moon is observed from two places on Earth, L and R, at distance B. The parallactic angle theta is measured, and angle theta will be equal to arc B upon radius D, and this is distance of the moon. So distance of the moon will be equal to B upon theta. So using this relation, we can find out the distance of moon or any other planet. Now, finding diameter of a distant planet or moon. So here we want to find out diameter of the moon. So what we do is, here we will observe the diameter, the opposite ends of moon from one point on the Earth. So one direction is along this, the other one is along this, and we can measure this angle. This angle theta can be measured, and if you know the distance between the Earth and the moon, then using the relation for angle, we can calculate D. This is what we are going to do. So let's see here. The angle theta subtended by the diameter at the observation point is measured, and if the distance of the moon from the Earth S is known, then this diameter will be S into theta, and using this we can find out the distance. And one very important thing, you will have to convert angles to radians and radians to angles and degree to minute, second and all that. So let us look at this example. Convert 2 degree, 15 minute and 30 second to second. Convert the same to minute and convert the same to radian. So let's do them one by one. And before I start, you can have a look. You know that 1 degree is equal to 60 minute and 1 minute is equal to 60 second. See, this single prime is minute and double prime is second. Now, here the first part is to convert it to second. So what we do is convert everything to second. So 2 degree will be 2 into 60 into 60 second. 15 minute will be equal to 15 into 60, and 30 second is already there, and multiply and add them, you get 8130 second. Now for the second one, convert the same to the 2 minute. So let's see what we get now. Here, see, convert this 2 degree to minute. So 2 into 60, and 15 minute is already there, so no need to change, and convert 30 second to minute. So you divide by 60 and add them all, you get 135.5 minute. And now the next one is convert the same to radian. And to convert them into radian, first we must convert them to degree. So you see, this 2 degree is already there as degree. 15 minute will be 15 upon 60 in degree, and 30 second to degree will be 30 second upon 60 into 60. So this is in degree, this is in degree, this is in degree. Add them up, you get 2.258 degree. And then you know that 180 degree is equal to pi radian. So from here, 1 degree will be equal to pi upon 180 radian. And if that is so, then 2.258 degree. See, 1 degree is this much. So these many degrees will be, multiply this by this angle. So you get 2.258 degree is equal to pi. Put the value of pi, 3.14 upon 180 into 2.258, and this product will be in radian. And when you simplify, you get 0.0394 radian. See, in all such relations, the angle theta will be used in radian only, because that is the SI unit. You cannot use degree or minute or second. So you must learn to convert them to degree. So let us begin with a numerical problem here. Okay, a very simple problem. The planet Jupiter is at 825 million kilometers away from the Earth, and the angular diameter of Jupiter is 35.72 second. Calculate the diameter of the Jupiter. See, this diameter you have to calculate, and this angle theta is known to us, and the distance s is also known to us. So this angle theta will be equal to diameter d upon s. So diameter d will be equal to s into theta. This is what I am using here. So here s is given to be 825 million kilometer away. So convert it to SI unit. 825 million is 10 to the power 6. Kilometer, kilo means 10 to the power 3 meter. So that is the total distance, and angle theta is 35.72 second. So this second can be converted to radian. So here, see, put the value of the distance. This is 825, and the powers are added up into 10 to the power 9, and this second is second divided by 60 into 60. This whole thing has been converted to degree and into pi by 18. So this has become radian, and multiply them. So the angle theta is expressed in radian, and you get 1.43 into 10 to the power 8 meter. This is the diameter of the Jupiter. And the next problem, the moon is observed from two diametrically opposite points on the earth. The angle subtended at the moon is the angle subtended at the moon is 1 degree 50 minute. Estimate the distance of the moon from the earth. So the diagram is clear. This is your earth, 1 point here, 1 point here, moon is here, and this angle is given 1 degree 50 minute, and this distance, this is diameter of the earth that you can find out, and you can calculate the distance of the moon. So now look at it. Radius of the earth is 6.4 into 10 to the power 6 meter, and diameter of earth will be double of it. So this is 12.8 into 10 to the power 6 meter, and the angle theta is 1 degree 50 minute. So 1 degree as it is, and 50 मिनट को आप डिग्री में कन्वर्ट कर लीजिए, डिवाइड बाई 60, सिंप्लीफाई, यू गेट 1.833 डिग्री. डिग्री को कन्वर्ट करेंगे रेडियन में, सो मल्टीप्लाई इट बाई पाई अपॉन 180 and then put the values in this relation. So distance of the moon will be diameter of the earth and angle theta. So putting all the values and simplifying, you get distance of the moon as 4 into 10 to the power 8 meter. And now echo method for measuring large distances. So supposing echo, you understand, the returning of waves, प्रतिध्वनि हिंदी में कहते हैं इसको. So supposing that you fire a gun and this is a hill, so the sound wave will go, hit the hill and return back. So it will the sound wave takes time to reach here and same time to return back. So the total time and the total distance traveled can be calculated if you know the speed of the sound wave. So here, see, velocity of sound wave is known. See, if the velocity of sound wave is known and the distance of the hill from the observer is s and the total time taken is t. So you use the simple formula that distance is velocity into time. S is equal to velocity v into time, and total distance is s plus s 2s. So total distance is 2s. So actual distance will be half of it, and the actual distance is this actual distance will be equal to velocity of sound wave into time taken divided by 2. And the same echo method is used when we can use laser, and you can use laser to find out distance of moon from the earth or other distant planets. Now what is laser? Laser is a monochromatic intense unidirectional beam of light. So laser is basically light and its speed is 3 into 10 raised to the power 8 meter per second, right? So if say this is moon and we are on earth, send laser beam, it will take some time to go and then it is reflected back, and you can calculate the time, and using the same method we can find out distance of the moon or any distant planet. Similarly, we use radar method to track for aeroplane navigation. So what we do is, say if you have some aeroplane and then radar, so microwaves are sent towards the plane and they are returned back and the time is noted, and from using that you can calculate the distance of the aeroplane and you can locate it. So echo method is used. Very simple idea, nothing special about it. And with this I come to the end of this unit. Thank you very much for watching it.